All right. We didn't quite finish the notes. There's not much I want to say about random variables, but we should just clarify, maybe just call it review. We talked about random variables, expected values, and variances. I did my best to try to pick some assignment questions to show where it might be useful. I was not very successful, so there you go. I tried. All right. We had a random variable x, and we can find the expectation of x plus x, which is 2 times the expected value of x, which means that you can just pull the 2 outside, essentially, is how it behaves. And then this is the one that I didn't really want to talk about, is where if we assume that the x's are independent, then we just multiply by 2, but I don't like that one. I don't want you to remember that one really. So if I'm going to make you do something, it's going to be the kind of the harder one, where we do not assume independence of the x's, which means that if you have 2x inside, to pull that the variance onto the random variable x, then the property is that you square the outside. Okay, so pulling the variance onto the x squares the coefficient. Okay, and that's what I want you to see, okay, and use and remember. And I didn't like that they kept coming back to this special case. Let's focus on this case. Okay. Just a little, continuous distributions are more of a segue into chapter 4. Okay, so which is what we want to start today, but it's kind of laying the foundation. So what we've been talking about are discrete distributions, right? Discrete outcomes. I roll a die, I can get a 1, 2, 3, 4, 5, 6, right? And those are discrete outcomes. But now we have continuous outcomes, things like heights. Heights are a pretty standard thing that we talk about. And so if we make a histogram of some sample of US adult heights, then we would get something that looks like this. What we're going to be leveraging, okay, especially starting in chapter 4, but also for the remainder of the course. So this is important information, I guess, is that to find probabilities are areas under the curve. Okay, and so I'll jot that down. So probabilities are areas under the curve. If you've taken any sort of calculus, or I guess Calc 2, then you know that you would have to apply integration, and integration is hard. And so we don't do that here. We've got kind of shortcuts that we use, and so you don't have to do that, but technically what we're doing is we're integrating over some interval. That's fine if we haven't. Do you guys take calculus? No. Yeah, some? Okay. Anyways, integration, not that fun. We don't need to do it, but we're kind of doing it, but not really. Okay, but the most important part is that the probabilities are now going to be areas under the curve. Okay? So what we're looking at here is the probability that a randomly sampled US adult is between 180 centimeters and 185 centimeters. Okay, so we've got this range of heights that we're interested in, right? 180 to 185. And to find the probability, we find the area under the curve. What do you think the total area under the curve has to be? If it's all a probability and I'm going from negative infinity to positive infinity, has to be 1, right? And so that therefore, I'll put it in green. Therefore, the total area under the curve is 1. Going back to those probability facts. Right. Okay, nice. So we're not just going to have these histograms. We're going to be thinking about populations, which means that we would have the entire population, which would kind of smooth out these histograms. And so now we get this probability density function. That's, I'm not going to refer to it as that, but that's what it's called when it's this kind of smoothed out function. So we can use this function. So this function, that smooth one, the smooth line is what we would integrate if we were to use calculus, right? If we were just looking at the histogram, we can figure out the heights of all the bars, and we can do that. We can kind of manhandle it a little bit and get there, but we won't need to. Okay. One of the things to keep in mind is that because the probability is the area under the curve, if you have a distance of 0, right? If you think about a rectangle, right? Then if you have a base of 0, then how big is your rectangle? What's the area of your rectangle? It has to be 0, right? Because one of the sides is 0. And so the probability, and this is kind of like, I don't know, weird thing to think about, okay? But every individual outcome, the probability of that happening is 0, right? They all still happen, but on little increments, right? Little ranges. Okay? So that's kind of fun, I think. Think about rectangle. All right, the base times the height. But if b is equal to 0, the area is also 0. And the area under the curve is the probability, so the probability of a single thing is 0. Fun. How about some real, our first distribution, the normal distribution. We've already seen it. Let's see here. And I talked a big talk. I said, okay, heads up, we're going to do 4.3 before we do 4.2. But then I was going through it and it relies on an example from 4.2. So I'm going to do it in the proper order. That's okay. Feels better too, I think. All right, the normal distribution. We've seen it already. We know what it looks like. It's unimodal and symmetric. Oh, that's ringing a bell. Haha, bell-shaped curve. That was an unexpected pun, but a pun nonetheless. So we call it a bell-shaped curve or a normal distribution, and I like to call it, I like to capitalize the N. That's only to emphasize that it's a name, and I think I've mentioned that before, but I often capitalize to emphasize that it's a name. Okay. The reason we start here is because a lot of things can be modeled by a normal distribution. Okay? And so when we're modeling, usually what we're doing is we're finding probabilities, we're making predictions, and doing all kinds of things. And so knowing the shape of that distribution and how it behaves is really useful. Yeah. Some notation that we use is a capital N to denote the normal distribution. The normal is also called the Gaussian distribution, but it doesn't have that same ring to it from Gauss. Let me see here. I'll blow this up. This N, shows that it's a normal distribution. So how you read it is it's a normal distribution with a mean of mu and a standard deviation of sigma. With a mean mu and standard deviation sigma. We only touched on these Greek letters just ever so briefly. We've seen them, they've kind of been lingering, but now they're here to stay. And so one thing to remember is for the Greek letters, they always describe the population. And so Greek letters are parameters, which means they describe the population. So if you know the mean and the standard deviation of the population of US adults, for example, then you can find probabilities associated with finding someone who's, I don't know, 6 feet tall, right? It's the probability of being taller than that, right? And so that's where we're headed. This also goes back to describing a distribution, right? We needed to know the shape. Well, it's normal. We needed to know the center, mu, and we needed to know the spread, right? The standard deviation. So now we've fully described this distribution. Here's just kind of a, I don't know, kind of a fun look at the distributions. And so I guess they've analyzed heights on OkCupid. Is that even around anymore? I don't know. Maybe not. Other things took over. But anyways, so there's a distribution, there's a shift in the distribution. So here, what we're looking at, and I think it's extra funny that they used yoink. Hello? I'll just go in and mute everyone. Let's see here. How do I? Sure. Okay. Hello? Okay, so we know the distribution of US adults, and then that's this faint line here. And then looks like everyone just kind of made themselves a little taller. But also there's this kind of interesting shift where they talk about starting at roughly 5'8". So this is for the man. You're so close. So then you bump it up a little bit more, and there's this shift in the distribution. It's just kind of a fun look. They see it in the females as well, but there's not that kind of the jump towards being taller. It's just everyone made themselves taller, I guess. Or maybe we all shrunk and we didn't know it. How about that? So what we're going to be looking at is different normal distributions, and we're going to have different centers, different spreads, right? And so what they're going to look like, even though these look the same, right? How would you describe those distributions? I would describe the first one Well, it looks like a normal distribution to me, centered on 0, and we're told that the standard deviation is 1. We haven't really dug any deeper than that, so that's okay, right? But the spread is between -3 and 3, right? Using what we've learned so far. Whereas the second one, same normal distribution, I'm fine with that. But this one looks like it's centered around 19, and it goes from 7 to 31, right? So we've got a different spread and a different center. So if you look at them individually, they're going to look the same, right? Because they have the same shape. But if you put them on the same scale, right? If you have a wider spread here, right, things are kind of going to flatten out, okay? And so why? Because the total area has to be 1. So the total area is always the same. So if you've got a tight spread, then everything's up in that peak, and everything's all concentrated here, right? Whereas if I need to spread out an area of 1, but I have to cover a larger range, right, a larger spread, then it kind of flattens down. Okay. And so here, let's do this. Larger spread, right? And let's remember that the total area is 1. Is still 1. When would we use this? Well, we use it to compare different distributions. We use it to compare observations from different distributions. Okay. And so the standard example is the SATs versus the ACTs. I didn't write either of those because we're not in the States, but maybe you have, right? And so the scores are on different scales, okay? And so the SAT scores are nearly normal, distributed nearly normally, but nearly normally distributed with a mean of 1,500 and a standard deviation of 300. Okay, so we know the shape, we know the center, and we know the spread. That's good. Whereas the ACTs have a mean of 21 and a standard deviation of 5, right? So you can't compare them straight across. What would you have to do? You'd have to standardize them, and that's what we're going to do. So, of course, a college admissions officer wants to determine which of the 2 applicants scored better on their standardized test with respect to the other test takers. Pam, who earned 1,800 on her SATs, way to go, Pam, or Jim, who scored 24 on his ACTs. Okay. So what we're going to do is I always encourage you to draw the graph. Now, that's not going to make sense for a long time, but if you keep doing it, it will be helpful eventually. It's one of those things. So I would draw this normal distribution. Just doesn't matter any width, any height, whatever. It's just the shape that you're drawing. And then what do? I have to put, I'm going to put the center here. And then there's not really a place to put the spread. So what I do is I jot it down underneath. I say that the spread was 300 because these are the SAT scores. Jumping over to the ACT scores, which Jim wrote. Oops, that was a terrible. Should start at 21 and go up. We were told it had a mean of 21 and a standard deviation of 5. So I'm just going to jot that down. Now, Pam had a score of 1,800. So what we're going to do is first off recognize that this is just a number line, right? And it's centered on 1500, but we all understand that there's a lot of people that get less than 1500. There's a lot of people that get more than 1500. In fact, how many? 50-50, right? Because the total area is 1, right? What's the probability? We can even do that. What's the probability of scoring less than 1500 on your SATs? 0.5, right? Because it's half the area and we know the total area is 1, right? And so we already know how to answer some probability questions. Okay. Now, Pam scored higher than that. So we want to know, okay, how much higher relative to the mean, right? How much higher than the mean did she score compared to Jim, who also scored above the mean, right? But we have to take into account the spread, and that's it. Yeah. I was this close to writing all this out, and then I remembered there's a slide for that. There's a slide for that. Okay, so we can't just compare the raw scores because they're not on the same scale, and that's okay, right? So then we compare how many standard deviations beyond the mean each observation is. Yeah. Even without this showing here, right? Let's go back to where we were here, for example. If I asked you how many standard deviations, I'll scroll up so you can see, how many standard deviations was Pam above the mean? You know how to solve that, right? Might not do it kind of immediately, but what would you do? You would want to find, okay, how do I problem solve this? You would say, okay, well, first thing I should probably find this distance, right? The distance between 1800 and 1500. Fair enough, right? Then I want to know how many 300s I can fit in that distance. Conveniently, 1, right? And so same thing with Jim. If I wanted to know how many standard deviations his score, which was 24, I'll put that on here. Oops, try to put that on here, 24. How many standard deviations is 24 above 21 if the standard deviation is 5? Now I've got a distance, I've gone a distance of 3 over 5. Oh boy, not very nice. But less than 1, yeah? It's all worked out here, so that's why I'm not writing it down. So we found that Pam score, right? We found the distance. Here's the distance from the mean. And then we divided by the standard deviation, right? To find how many standard deviations away from the mean is this observation. And so we found that it's 1 standard deviation above the mean, right? You could be 1 standard deviation below the mean, right? If you scored what? If you scored 1200, 1500 minus 300, 1200, right? Which is still okay. Then we did Jim's score, and we didn't end up at a nice number, but we did end up at a distance of 3 over 5, which is 0.6 standard deviations above the mean. Now, what have we done here? We've standardized everything so it's on the same scale, right? Now we're talking about distances from the mean. How many standard deviations from the mean? So what we've done is we've converted to this standard normal distribution. The standard normal distribution still is normal in shape. All we did was shrink both of those distributions down, right? not visually, but kind of in spirit. And then what did we do? We took every observation and figured out how the distance from the mean, how many standard deviations from the mean, which makes the center 0, right? How far is 1500 from 1500? 0 standard deviations away. How far is 21 from 21? 0 standard deviations away. So now we're centered on 0. And as a fact, the standard deviation on the standard normal is 1. Okay? Because we've converted all these observations to be the distances in terms of the standard deviations. So now, when they're all on the same scale and on the same curve, now we can plot them and say that, okay, Pam was 1 standard deviation away, whereas Jim was only 0.6 standard deviations above the mean, making Pam's test score better, right? Usually a higher score is better, right? Regardless of the SATs or the ACTs. Right? Depends on the scenario, but usually, right? Nice. I overwhelmed you with formula sheets just because I hadn't merged them all yet. I'll put everything, there's a lot of overlap on there, right? And so you've got 2 sheets. I'll put them all on one, but wanted you to have, well, I wanted you to have both of them. See what's going on. But the Z is how we denote this standardized value. So we're going to be talking about Z scores, and you might have seen Z scores in the past, okay? And they're just standardized values taking into account the mean and the standard deviation. Now, the order that we're going to find the distance is always going to be the observation minus the mean. Okay. So in terms of our formula sheet, it'll say x minus mu over sigma. Right? Because the observation's always going to go first. Why would we care about the order if we're just finding the distance from the mean? Well, we are, but we're also wanting to know if it's below the mean or above the mean, right? So now any observation that's below the mean, so if x is less than mu, right, then I get a negative value, right? So negative z's, going back here, right, to the left of 0, now we get negative z values. Okay. So here, negative, can I refer to something that's introduced on the next slide? That's rude. But I'm jumping around, so that's even ruder, I guess. Negative Z scores indicate the observation is below the mean. Below the mean. All right. So we're gonna have negative values, positive values, and it just shows us where it is relative to the mean, right? But that's why it's important to do the observation minus the mean, because otherwise you'll flip it around, right? The distance is the same. It's just whether it's above or below. Yeah. Okay. Z scores we can use in any situation, okay? But usually we use Z scores to find probabilities. And so then we have to have a normal distribution, okay? But you can standardize values and still find the mean and the standard deviation of any distribution. It just won't be a good measure of center and spread, right? And so you can still use it, but only oops, I'll use this. When the distribution is normal, can we use z-scores to calculate percentiles? Percentiles, sounds like something to do with probabilities. That's a bit of a stretch, right? But what am I relying on? All the three P's are the same. Probabilities, percentages, proportions, all those words. I can switcheroo, right? So percentiles, probably something to do with areas under the curve. We'll see it on the next slide, I think. But before we do, one thing to keep in mind is, as a rule of thumb, any observations that it's more than 2 standard deviations away from the mean will be considered unusual. Okay? And in stats, that's all we care about, are these unusual observations, right? Did I find an extremely large rat or no, right? I don't care if I found a normal size rat, right? Or average size rat. I want to know if I have an extremely large rat. I don't know why rats came to mind. Someone told me about, is it pocket gophers? They sound cute, but they're not. Anyways, digress. But as a rule, okay, this is going to come in handy. Now we mean the absolute value of Z. Why? Because I could go below the mean 2 standard deviations, or I could go above the mean 2 standard deviations. And so here on this normal distribution, don't have to go too crazy, draw the general shape. Centered on 0, I'm drawing the standard normal distribution, right? With a standard deviation of 1, because it's easier, right? If I've gone to Z equal to negative 12, yikes. That would be nuts. It can happen, but it's unlikely. So what we're going to say is that any values kind of roughly between a Z of -2 and +2, these are all kind of usual values. Things you wouldn't be that excited about. There's nothing unusual about them, right? Whereas here in this region, we start to think of them as unusual values, right? Why? If the area under the curve is the probability and the curve is getting smaller and smaller and smaller, then the probability of those things is getting smaller and smaller and smaller. Whew. Yikes. Hey, I thought this was going to be a fun course, Emily. What's this all about? But once you get the hang of this, and we're going to be doing this a lot, then we're off to the races. Yeah. So here, right, recognizing that the area in the tails is getting smaller, and so we've just decided on a cutoff point, and 2 is usually where we start to get a little suspicious, right? So here I'll clarify, since the area under the curve is small here, right, which is the probability. We'll come back to that. Percentiles, as promised. Often we talk about percentiles when we talk about things like IQ and baby weights and things like that, right? You want to be in the top percentile, right? And so the percentile is the percentage of observations that fall below a given data point, okay? And so usually right? If I say I'm in the 10th percentile, right, for IQ, sounds good, but it's not, right? What does that mean? It means that 10% of the population is below me. Uh-oh. So 90% of the population is above me, right? And so you want to be really careful when you talk about percentiles, right? It's always the amount below that value, right? And so here we could talk about, we could talk about, this looks like Pam's percentile, right? She's got some percentage or probability or area under the curve below 1800, right? And so this area, because this was Pam here, this area is the percentile of Pam's score. Finding those areas, let me go back here. This was much nicer to look at. Finding these areas, that's where we would need calculus, right? Or software, sounds nice, right? That's how we should be doing it. But because we're a pen and paper establishment, can't do that. And so we're kicking it old school with these terrible Z tables, which I try to avoid like the plague. I think it's really, well, I know it's very archaic, but here we are. So I think I'll split this pile. This one I have lots of, and can pass them around so that you can see it.
Do you have a digital version of this so we could use it at home for practice or not?
Yeah.
Oh, perfect.
Yeah.
Okay.
Yeah, well, the function for the normal distribution is quite nasty.
Right.
And so that's why the Z tables originated. They're like, I don't want to do this. Let's just do it once, make a table. But we should be using software. That's what we should be doing.
So what does Z actually mean? What does it represent?
It's the number of standard deviations away from the mean.
Okay.
Yeah. The Z itself, I don't know where it came from. Thank you. Anyone not get one? Anyone want extras? I've got extras. That's an option. You can grab them later. Okay, so now you've got this, so much paper. Yikes. Z tables, okay, terrible things. But this is how we're gonna find the areas under the curve. Okay, so what I wanna do is, okay. I flip-flop back and forth. They have R code in here. R is a statistical programming language that we don't make you learn, but it's healthy to have seen it. Okay, it's not that scary. P-norm command, 1800, you give it the mean, the standard deviation, and it gives you the area to the left of 1800. Okay. We're gonna do it in Excel, so it's not that different. They just didn't have any pre-made Excel ones, so we'll see it in the lab next week. But I'll make a note here. We will use Excel in the lab, but it's gonna take all those components, right? It needs the observation, it needs the mean, it needs the standard deviation to do what? To calculate the z-score. And then it does some secret magic behind the scenes and it returns the area to the left. And so here it returns the area to the left of 1800 in this case, right? This first value. Can't remember if the Excel command is pnorm. I feel like it's something similar. Okay, but we're stuck here with a Z table. So you've got something that looks like this. There's lots of different kind of layers on the Z table, but we'll be using something that looks like this. And so first thing you're gonna notice is there's a front page and a back page, okay? Of course, the Z distribution is centered on 0. There's negative values, there's positive values. So there's a negative side and a positive side of the Zs. So that's the first thing you wanna be keeping track of, okay? Notice there is a positive and negative side. I wonder if I have, let me just see if I can grab. I feel like I have it close, somewhat close by. Here, I'm gonna open this. So this is the one that I handed out. I don't think I have this posted on Moodle yet, but I will. That's how much I hate the Z tables. Starting here on the negative value of Z, and then it's increasing as you move down, and the anatomy of it, let me see here. I want to copy, and I want to throw them in here. Paste. Hey, nice. I did it. Technology. Okay. So, all right, we've got this negative side, positive side. Let's just break down what it's doing because it looks terribly overwhelming, right? When you first look at it, but all it's doing is it's broken up the number line on increments of hundreds, so 2 decimal places. You could go further if you want to, but the table would be huge, right? And so, so what we need to do is we need to match up the whole value of Z with the first decimal place with the second decimal place in the table. At the intersection, so let's say, for example, Z is, let's say -1, or let's do something bigger so I don't have to scroll so much. 2.53. That's a Z. That could happen. So you found that your observation is 2.53 standard deviations below the mean. Yeah. What's the probability of finding something smaller than that? Right. Then what do we want? And when do we want it? Centered on 0, -2.53. I want to know what that area is because I'm trying to find the probability. It's just a made up example, so I can do whatever I want. Starting off nice and slow. Whole number in the first decimal place in the left-hand column, which puts me here. I like this one because it's got the shaded regions. Otherwise, your eyes jump all over, right? Or if you take a piece of paper, just make sure that you're not jumping around. Okay. And then the second decimal place was 3, which means that at the intersection here, and you should confirm on your table, they're the same. The area to the left is 0.0057, or the probability is 0.0057 of being less than that z-score. Okay. And so now I can replace my question mark with 0.0057. Probabilities have to be between 0 and 1, right? Probability of 0, well, it means it can never happen. Or the total area under the curve is 1, right? Or something in between. If we know that the area to the left is 0.0057, and we know the total area is 1, right? We can use these as little puzzle pieces. What's the probability of an observation greater than the one we saw? Right? This is going to have to be, this area here has to be 1 minus 0.0057, which, thank you. Right. So the probability of seeing something larger than that is 99.43%, right? Usually we convert to percentages, or 0.9943 if we're still talking probabilities, or proportions, right? All those, you have to be really flexible on the wording because they all mean the same thing. Okay? So at some point, they decided, so way back before computers, obviously, way before, someone decided to sit down and do all these integrations, right? So many, right? Each one of these would be an integration. So someone said, you know what? I'm just going to sit down and do this, spend the afternoon, and come up with this table. And then everyone said, oh, thank you. I've never wanted to do that again. But at some point, they decided that's probably enough, right? And those points were negative 3.49 and 3.49, okay? After that, what happens? Let me add a page here. Maybe I should do it after this one. Yeah. So hey, that's not bad. If I have Z, which is centered on 0 with a standard deviation of 1, the table goes from 3.49 or negative 3.49 to positive 3.49. Fun fact about Z is that it technically goes from negative infinity to positive infinity, meaning anything can happen, right? But it's just extremely unlikely. Unlikely as shown by the area in the tails, right? And so here, Z continues in both directions, but at some point they said, well, let's see here. At negative 3.49, the area to the left of that is 0.0002. That's really small, right? How about if you reach something more extreme than that, right? More into the tail than that, you can just say the probability is less than 0.0002, right? Now we can use software to find the more exact values, but think we can all agree that once you have a probability of 0.0002, anything beyond that, you can just say less than 0.0002, right? And so, for example, there's always one question that I get a lot of questions about. I found a Z of 12. That can't be. Well, it can, but it's very unlikely, right? And so here, if I found a Z of, let's make it negative 12, right? All you need to say is that the probability of seeing something less than a Z of negative 12, well, at that point, you can say it's approximately 0. It's not 0 because the tails keep going, but it's definitely less than 0.0002. Okay, and so here, for values less than Z equal to negative 3.49, we say the probability is just the probability slash area to the left is less than 0.0002. So just as an example, the probability, I'm going to jump right in, the probability that Z is less than negative 12. Uh-oh. I thought we were done with probabilities. Well, we are and we aren't. Probability notation we're going to keep using. The probability that Z is, you can do less than or equal to negative 12. Can it be equal to negative 12? No, it can't, right? Because it has to be on some sort of width, right? And so, sure, is less than 0.0002, or the probability that Z is less than or equal to negative 12 is approximately 0. I'm going to be really, really strict on the approximately 0. Okay. And so here, oops, must say approximately 0. Since the tails continue to negative infinity, they never touch the axis, which is extra confusing because we know the total area is 1, right? It's one of those kind of mind-boggling situations where it never closes on the axis, but it gets really, really close, and then the total area is 1. And so we must say approximately 0 since the tails extend to plus minus infinity.
Is this Z table universal?
Yeah, there's some different ones where they drop the negative side, but and sometimes they only use one decimal place, but
Right.
but the probabilities are the same.
So
Yeah.
like we could use this on homework questions.
Yeah.
This is a good reference.
Yeah. Totally. Yeah, that's the one that I'm going to be going off of. Good. So I'm a real stickler for that approximately, right? Because the tails keep going and going and going, just very little area, right? There's already very little area after negative 3.49, right? 0.0002. Without using the table, but I mean, you can if you want. What's the probability area under the curve? Okay, got it. Of a Z score greater than 3.49. Greater than or equal to 3.49. Keep in mind there's symmetry around the mean, right? So if you know that, well, the tail area from negative 3.49, I already know is 0.0002. So then by symmetry, this must also be 0.002, which we can leverage as well. We can leverage that symmetry. If I have the same Z-score because it's centered on 0, just a positive and a negative version, then I know the other side as well, which is what some Z tables have said. Well, if I give you one, you know the other one, right? Just by symmetry, you know? But I'll be using this one. Or using the table, now I need to make sure I'm on the positive Z value side, right? And so now it goes down to 3.49 or 3.4, and then the second decimal place here is 9. That's going to be the area to the left again, right? So I like this table of all the tables because it has this kind of handy guide telling you that, hey, the table entry and these guys, let's see here. When it says table entry, it's referring to these values. Those are the table entries. Okay, so when I say table entry, I mean those probabilities or areas under the curve. Okay. So some Z-score that you feed it, it'll give you the area to the left. Okay. It even specifies more, but as you get more comfortable, these will be helpful, but right now they're probably maybe just overwhelming. That's okay. That's okay, she says. So what's this area? 3.49, now we're on the positive side, but it always gives you the area to the left. So it's up to you if you need the area to the right. And usually how I draw these areas, because shading gets a little messy, I draw a bar up and then I draw the areas above it. I mean, technically what I could be doing is going like this to indicate that it's everything to the left. But if I want to slice it and dice it, it gets messy, so I don't do that. But from the table, oops, this area is 0.9998. Well, wouldn't you know, the total area is still 1. So if you have the area to the left, you have the area to the right. This must be 1 minus 0.9998, which is 0.0002. Which is the same. However you got there is great. Okay. Just recognizing that you can break up the space or the area under the curve into puzzle pieces that you want. Okay. And then this is one of those things where whatever you are drawn towards, whatever you do naturally, just do that, right? Whether it's using just the symmetry, maybe you never ever want to look at the positive side of the Z table, or maybe the negative, I don't know. Well, then you'd have to rely on symmetry, right? You can do that, it's fine. Or you just want to use the Z table as is. Either way, you're using the Z table. So, okay. Kept this in here because I think I mentioned Six Sigma. And so it's this notion that if you move out, or if you have a spread of 6 standard deviations, right, 6 sigma, then practically no items will fail to meet specifications. And that's just relying on a fact of the standard normal distribution, or the normal distribution, any normal distribution. Hey, what's the difference? Different means, different spreads. The standard normal has a mean of 0 and a spread of 1, right? I've just shrunk it down. Let's do an example. How much time do I have? Just enough. At Heinz Ketchup Factory, the amounts which go into bottles of ketchup are supposed to be normally distributed with a mean of 36 ounces and a standard deviation of 0.11 ounces. Everyone understands you go to the store, you pick up a beautiful bottle of Heinz ketchup, and it says it's 36 ounces, but that's on average. And so we have this kind of internal mechanism that says, oh, this was a really heavy bottle of Heinz, right? It's overfilled. Or usually we don't react to that. Usually we react to, this isn't full, right? And so now we're going to be able to find probabilities associated with that, which is how you make the claim that I got an underfull bottle of ketchup, right? Which is also what the quality control team is trying to avoid. So once every 30 minutes, a bottle is selected from the production line. Seems excessive, but whatever. And its contents are noted precisely. If the amount of ketchup in the bottle is below 35.8 ounces or above 36.2 ounces, they don't want to be overfilling and they're just losing money. Then the bottle fails the quality control inspection. What percent of bottles have less than 35.8 ounces of ketchup? Okay, give you just a minute to either in your brain or on paper, sketch out the curve given this information. Just a minute. Let you fly on your own. I'll highlight what you need. Shape, center, spread, and then some gibberish. And we want to know what percent, but a percent is just a probability. So what area under the curve have less than 35.8 ounces of ketchup? Okay, I'm impatient. So here we go. Normally distributed, I'll start with the shape. That's a good place to start. Close enough. Then I can draw my center. Centered on 36. I'll put mu equals 36. And then somewhere around there, I like to put sigma as 0.11. It's more of a note. I don't incorporate it into my drawing. That would be too much work. Now, 35.8, it makes sense that it's below the mean, right? And so, right, because you're underfilling, you're allowed to be a little bit under 36, but not too far. And so here, this is the observation that we're interested in. Right, the observation that I want to find the associated probability with. So I'm going to put that. No one likes it when I put it that far out, but it's just to visualize things. Okay, so you're not doing anything to scale really. As long as you're on the correct side of the mean, then you're okay, right? So 35.8 is your observation, which is X on your formula sheet. So I'll start using that. Okay, now I want to know what percent of bottles have less than 35.8 ounces. So everything below 35.8, there's some area and we need to find it. We don't have a table with a mean of 36 and a standard deviation of 0.11. How many tables would you have? You'd have an infinite amount. so many combinations, it's crazy. Right, so we don't do that. That is logical. So first step, you have to standardize it, right? Because we do have a Z table, so I need a Z. Okay? So step one, draw the graph. Whee! In terms of part marks, I know everyone loves part marks. I want you to draw the graph, not for marks, but if you've done it, if you've drawn your graph incorrectly, but followed through on the graph and it looks, you know, reasonable, then I'm not that upset about that, right? If you go against what you told me you were going to do in your graph, that's weird, right? So as long as you tell me what you're about to do and then you do it, even if that was wrong or kind of minorly wrong, then that's okay, right? So draw the graph, always draw the graph, even if it doesn't make sense to you yet, it will. Step two, calculate Z. From the formula sheet, Z is X minus mu over sigma, which means it's important to keep track of which one is your X and which one is your mu, right? But also kind of logic will dictate that I'm going to have a negative Z score, right? Because I'm expecting 3.58 to be below the mean, right? So then I have 35.8. I think I said something wrong earlier. 36. I said 3.58. Minus 36. How far is 35.8 from 36 with a standard deviation of 0.11? Well, it's going to be negative 1.81818 repeating. Now, as a rule, so that's your Z, that's fine. If you have software, it would be able to handle that. But our table only has 2 decimal places, right? And so that means that you have to round properly to 2 decimal places. So I'm going to add a page here. I'll make it a step. Round Z properly. I don't think I have to say that, but I don't think. To 2 decimal places. I usually abbreviate decimal places to DP. I don't think I'm alone in that, but I'll introduce it here. So then Z is negative 1.82, right? The 1 is followed by something greater than or equal to 5, so I have to round it up. And this is to match the table. So it's not something that you need to memorize. The table is going to prompt you, right? When you go to use it and you say, oh, well, I can only do 2 decimal places, so I need 2 decimal places. And now, step 4, use the Z table to find the area to the left. So what we're finding is the probability that Z is less than or equal to negative 1.82 from the table. I'm going to scroll up and grab a screenshot. Hey, where is it? The negative side. Negative 1.82. Don't like that one. is 0.0344. Scroll all the way down, 0.0344. And hey, I still have 2 minutes. You don't want to be rounding those probabilities. They've given you 4 decimal places of precision, and you should probably take it. Put that in there. I'll leave you with this practice problem where we'll pick up on Monday, I guess. Wow, crazy. Which bottles pass the quality control inspection? Now you're finding areas under the curve. You got it. We'll pick up there. If you have any questions, let me know. Otherwise, I'll see you on Monday.